Great. So welcome everyone to the last AI for Science seminar of the year. I'm very pleased to introduce today's AI for Science speaker, who is Prashant Singh, an assistant professor in the Division of Scientific Computing at Uppsala University, and also a SciLife Lab Fellow. So Prashant's research focuses on developing machine learning and optimization methods for fast, data-efficient analysis of scientific data, with a strong emphasis on life science applications. So prior to this, Prashant was an assistant professor at Umeå University and a postdoctoral researcher at Uppsala, where he also worked on machine learning and statistical sampling for computational biology. He received his PhD in computer science from Ghent and a master's in computer science from the University of Delhi. So please join me in welcoming Prashant.
Thank you so much, Rocio, and thank you so much for having me, Rocio and Simon. It is a pleasure to give the AI for Science seminar, and I think a good topic for the seminar is learning from noisy data under uncertainty, because this is a characteristic of scientific data. And noise in scientific data can manifest in different ways. So, for example, from microscopy data, and this is something that Rocio and I are working on together also, we see effects of chromatic aberrations in the lens, or sensor noise, or calibration noise in data from particle collider at CERN, which is another project that I have. There's noise from background events when you smash these protons together. On the right, you see noisy time series, which is proteins interacting in a circadian clock model as a stochastic system. And having just returned from California, I can confirm that my own circadian clock is definitely very noisy right now. So there is noise in scientific data, but in data in general, there is noise. Like when we do, and this is, for example, one of well-known data sets in machine learning called Food 101. Let's say we're trying to classify dishes, and this is hard enough for humans, right? So if I ask you to tell me whether the dish on the left and the dish on the right, which one is a pork chop and which one is a steak? It's not very easy to do so, and you can imagine what the machine learning model might struggle with, because then it's easy for the model to fixate on details in the background, like how the sauce is or how the dishes look. Another example, is this meat or is this fish? So there's ambiguity in images. And last one, fish versus meat. So the data quality itself can give rise to noise, like how the data has been captured, how it looks, and so on. So there is this inherent ambiguity in data, and the nature of it can be quite different in different types of data. It can also vary over time. And let's see how we can incorporate this in a machine learning setting. So the textbook machine learning problem is that we assume some IID data, which is Z's here, from some distribution P of X. And then we try to fit this data with model parameters data using the maximum likelihood principle. So we maximize the probability that the data fits the model, right? And you can also write this as minimizing the sum of negative log likelihoods, right? But in reality, data are often corrupted. They can be mislabeled. They can come from, let's say, having faults in how they were captured with a sensor or with a microscope, or different operators of these machines, like microscopes, might use them differently and induce certain shifts. Or you could also have adversarial corruption. Right, so this is captured in a more loose setting from the Huber's model, in which we say that the data comes from a mixture of the true distribution and a corrupting source. So the true one is P of Z, and the corrupted or corruption source is Q of Z. and epsilon is the corruption rate. And of course, we don't know epsilon, and we don't know q. So it's it's very hard for us to immediately say something or reason about them, right? So we approached this problem in the first work based on which am creating this presentation. What if we had a hidden indicator or a switch per sample which said whether or not this sample is clean or corrupted, right? So if the sample is clean, then we could have this variable ti, which is 1. If it's corrupted, then we could have it 0 so that it doesn't contribute to learning. And this would be nice, right? And this is what we explore in this paper from last year. So how we incorporate it is that the maximum likelihood simply extends with these indicator variables in this way, right? But the thing is that we don't observe TI, right? We don't know which ones are clean and which ones are not. So we must iterate over both possibilities and sort of try to infer them from the data. Okay, so to do this in a probabilistically correct way, we have to marginalize over all possible assignments of what TI can be, weighted by their prior probability. And since each sample has probability epsilon of being corrupted, we use a Bernoulli prior. So the blue sum here indicates that we're summing over all possible binary assignments, which gives us the marginal likelihood. But this sum is, of course, very hard to compute, so we must approximate it, and we do this using variational inference. So the first term that we get from this here is the pi-weighted data fit, and you will notice that we transition from indicator variables ti to a softer pi, which is a probability of being clean. So pi I is the probability that sample I is clean. So we transition into the elbow setting, and then we have 3 things which we will optimize over: the model parameters, the probabilities of being clean, and the level of corruption, which means that this approach is completely adaptive and parameter free, because we don't assume anything about epsilon. It is inferred from data, and the same for pi. Right, and this should be nice in practice, because this should allow us to adapt to varying noise levels. So after some algebra, which you will find in the paper, we arrive at this form of the loss function. And the key thing here is that we have a very simple way to optimize this objective using an EM style loop. In the expectation maximization, or the expectation step, we update the pi's, which is the probability that each sample is clean. And we show in the paper that this landscape is convex. In the M step, we update the thetas using the pi-weighted loss. And we do this until convergence. So even though we had these 2 things in the loss function, we still find that elegant way to do it without making any extra assumptions. So we tested it on some problems first on simpler model types. So this is linear regression. And since we began from the likelihood maximization principle, this approach extends to all problems that involve likelihood maximization, whether it be simpler models like linear regression to something like deep learning, which we'll get to in a bit. So we see here that this is, varying noise levels here, corruption levels. And the other approaches, I will not explain how they work, but the important thing to know is they all have to assume an upper bound on the noise level. So for them to work, we have to give this upper bound. And in our case, we don't need it. And we see that for varying noise level, our approach works quite well. And this continues if we vary the noise level dynamically. So what we do here is that we have a Birch distribution where the mean is at 0.1, and then we have a variance spread from 0.0 to 0.3. And then we randomly sample from this distribution the corruption level, basically. And the approach is able to estimate both the epsilon and pi on the fly and adjust accordingly. And so you see that the proposed method is sort of like able to account for this noise and stay quite accurate. Okay, but now we get to a small problem. And the thing is that with deep learning, these models are over-parameterized, which means that because they have such great learning capacity, they can memorize the noise. They'll eventually fit both clean and corrupted samples perfectly. So to address this, we have to lose some elegance. So this is where we have to introduce an additional thing here, that we rely on the validation estimates of the error. So we introduce a simple regularization, which is that we, or hard truncation. So once the model starts to overfit, and we detect this with the validation error, we discard samples with pi i's that are below a threshold. So basically, we say that samples that are not very likely at the moment to be clean will eventually, model will think they will be clean because the model will overfit, so we will truncate. And this threshold we determine using a statistical criterion. So we want to bound the type 2 error false positive rate at 5%. And so this is where sort of an annoyance comes in for us, that we wanted it to be completely parameter free, but for deep learning, we have to rely on this validation set and having this stopping criteria. But the result is that we are much more resilient towards noise. So this is CFAR 10 with 45% label noise, which is quite high. And you will see that with regularization that I described now, we're able to be at roughly 90% accuracy, whereas it drops substantially for no regularization, and even further if you don't do anything. Right, but these were all synthetic sort of experiments with artificially induced noise, but we also experimented with more real world noise. And this is the Food 101 data sets. So the estimated noise in this data set is roughly maybe 4% or so. And we show here results for varying noise levels. And these are some other approaches. So Jokor, which is the one in the screen shade, this one trains two networks that sort of teach each other and try to decipher which one is struggling more from the noise and sort of identify noise that way. USDNL uses uncertainty scores via dropout. Bear uses a Bayesian risk estimation principle, and CDR, if I remember, combines confident sample selection with some relabeling. And co-teaching also uses two networks to exchange information, like which samples were high confidence. So they're substantially more computationally involved than our approach. But we see that RLVI across varying noise levels does quite well. And the realistic case is something 3 to 5%, right? So we see that here both Jokor and RLVI are doing well. The only difference is that that one needs two networks, and we are sort of network free, but we need this dependence on type 2 error. Okay, so what we have is a versatile method because it works for any likelihood-based model. We can handle diverse corruption sources because we don't assume anything about epsilon or Q of X, which is the corruption source. We also saw that it is adaptive because if we change the corruption level, it is inferred automatically from the data, right? And it's also scalable. So it scales from linear models to deep learning. It scales from small data sets to large data sets. And it also can, it is applicable also to not just regression, but also something like PCA, right? Okay, but noise isn't just in the data, right? This was training a model from scratch, but often now we're in the era of foundation models, increasingly in science also. So then you're given a model, but its outputs, even clean inputs can give you sort of noisy predictions because the noise could be within the network itself, the epistemic uncertainty. So it is important to be able to quantify and say something about this. And this is something we explored in our recent work, which explores how do we quantify uncertainty in multimodal models. And in this case, we considered vision language models.
Prashant, at this point,
Yeah.
before you continue on that part, can I ask one of the questions from the chat?
Yes, yes,
So
definitely.
Stefano asked, how does the result depend on the specific kind of noise used, in particular Gaussian versus power law distributed noises?
Yeah, thank you for the question, Stefano. So the result does not depend on, if I go here, the result does not depend on the noise source. So if you see that we assume the Huber's model, which says that data comes from a mixture of the clean distribution and the corruption source, but we assume nothing about what the form of Q of X is, because we look at it at a more one versus all thing. So we have the clean and we have everything else. So you might even have a mixture of different corruption sources. So this could be actually Q1 of Z, Q2 of C, Q3 of Z, and so on. So we only care about P of C, which brings us to an interesting observation that this means essentially we are targeting the majority distribution, and that distribution is assumed to be clean. In robust statistics, we have this sort of limit in the sense that as long as the majority is clean, we will be okay. If, let's say, you have 51% corrupted data and 49% clean, then we will fail. Then all of the approaches that I present here will fail also. So we don't assume anything about the form of the corruption distribution, or actually even the P of C for that matter. We only assume that P of C or Z that come from P are IID because that's what we need for maximum likelihood. More questions?
Yeah, there's one more question that is asking if you could clarify why in RLVI you do not need an upper bound for epsilon, because you mentioned that for all the other methods you do.
Yes, we don't need an upper bound because what the value of epsilon is inferred from the data. So if we go to the formulation, here we still have epsilon, but also t's. Then we transition into elbow, where t's become pi's, but we still have epsilon. And then when we do the EM thing here, then you will see that we have actually gotten rid of epsilon at this point. So there's only pi's and thetas left. And that is because we have these two terms, in which the first term is the pi-weighted data fits, and the second term is sort of a KL divergence, which keeps the pi values consistent with the overall corruption level. So what we're saying here is that the epsilon, which is the corruption rate, has transitioned into or incorporated into this probabilistic representation of pi. So the probability that a sample is clean or corrupt, that in itself encodes what the corruption rate is what thing. Any more questions?
Simon just typed a question. I'm not sure if I can just ask. Yeah, go ahead.
I can also ask it. So I was just wondering if in the EM algorithm that you are specifying whether you have any guarantees of like convergence to a global minimum. I'm not sure if this is a resolved question. I remember when I learned about it, it was there was no guarantees about global optimality of the EM algorithm.
Yeah, that's an interesting question. So I think we only prove convexity in our objective. And then we use EM because it fits well, but we did not explore whether EM will give us global convergence for this. So I must check.
All right. Thanks.
Yeah, thank you. Okay. More questions or should I continue?
No, you should continue.
Okay, thank you. Okay, so yeah, in the second part, we want to explore. In the first part, we looked at, okay, but if you're going to train a machine learning model under noise, how do we do it well? And in the second part, we want to explore, okay, but what if we're given a pre-trained model, right? Then how do we work with the noise? And the first question that arises is, but okay, let's back up. So if there's a pre-trained model, it is deterministic. How do we estimate first the uncertainty that is within this model? Right, and we considered a very simplistic case of vision language models, starting with CLIP, and CLIP is from 2021, so it's not absolute state-of-the-art VLM, but it's a very good representation of how VLMs work. So VLMs embeds the two modalities, image and text, into a shared space where matching relies on this cosine similarities. And the model is trained to maximize similarities between matching pairs of image and text and minimize it for non-matching pairs. But of course, uncertainty can vary across different examples of these pairs. Some captions are more ambiguous than others. And uncertainty might mean very different things when it comes to text than images. And this is something we explore now. So we have two parts to our hypothesis. The first is that we argue that uncertainty in the text modality is mainly alloteric. And in case of the image component, it's mainly epistemic. And why I say this is that if you and I were to look at the scene I have outside the window, we could each describe it in maybe 10, 20 different ways based on our linguistic preferences and the phrases we like to use and so on. So this is uncertainty within the data itself, like within the text itself, or the process, which is me putting out this language. In case of the images, if I'm given an image of this scene that I see here, the image is what it is. If I am to model it, then the uncertainty comes from the modeling part of it. Right? So it's mainly epistemic. So we argue that these two cases should be dealt with differently. And the second thing that we say is that when we want to work with these pre-trained models involving cosine similarities, we should remember that these embeddings live on the unit hypersphere because of cosine similarities and the objective that they're trained with, right? So, okay, this is a bit pixelated here in the image that I saw, but this figure illustrates the conceptual difference. So if we look at the mapping from real-world objects to representations, CLIP uses deterministic one-to-one mappings for both modalities, text and image. There has been previous work, ProbVLM, which introduced probabilistic embeddings for both, but treating them symmetrically. So they just put a probabilistic adapter for both text and image. But that means that there is a small issue. So when I say a dog or a cat, what I mean is that it can be any dog and any cat. So in reality, this should map to infinite dogs in real life. But when I give an image of a dog or a cat, it is a specific dog or cat, an individual, right? So it should not map to a distribution of all dogs in some way. So this the asymmetricity is what we want to capture in some way. So what we do is that in this work, we only look at how to approach the textual modality. We put a probabilistic adapter on the textual modality, but we go back to our second hypothesis, which was that these embeddings live on a unit hypersphere. So then we should stay true to this and use directional distributions. And two such examples are von Mises Fischer and Power spheric to model this in a probabilistic way. And for images, we just keep the CLIP embeddings as they are, keep them deterministic for now. And then we adapt this by putting a text adapter here. So we only adapt the text and we let the image embedding straight through. Now, an intuitive point here is that when you put this adapter and when we use a spherical distribution for modeling this adapter, what we're doing is essentially putting a cone on top of a spherical surface. So when the uncertainty is low, this cone is very sharp. When it's high, then the cone is sort of like more spread out, give you an intuitive picture. For training it is nothing special. We use the same influence E style loss as they have in CLIP. But the only change that has happened is that we have this log likelihood matrix, or the kernel, if you will, here. And the same concept holds that for matching image text pairs, we want to maximize the similarity, and we want to minimize it for non-matching pairs, right? And then there's these two terms. The first is text to image, and then this is image to text. Okay. And when we derived sort of the form of the loss for the two spherical distributions that we consider, we see that it comes out to be like a natural extension to CLIP. So both are monotonically increasing functions of cosine similarity weighted by kappa, which is the concentration parameter. And this concentration parameter inversely relates to uncertainty. So when kappa is very high, meaning that the uncertainty is very low, we have the case where the output reduces to approximately CLIP's objective. And this is what we want. We want ASIM-VLM to be sort of like a graceful extension to CLIP, while maintaining sort of consistency with underlying principles. So we evaluated now on different data sets, and let's take a look at the results and let's walk them over together. So what we see here is recall for the CC200K dataset. And when the model is doing well, when the recall is high, you would want the uncertainty to be low, right? So this is the uncertainty level on the x-axis. So uncertainty should be low when the model is doing well, which we have for ASIM-VLM, these two cases. When the model is struggling, then you would expect the model uncertainty to be high. So you would want to be somewhere here. So you would want this monotonically decreasing trend that we see with our approach. And we see that other approaches don't have this same trend always, especially in image to text case. In text to image, they get better. Then in MS COCO, the approaches are closer together, but we still see that we have a good trend to how this uncertainty evolves over different levels. And I should also apologize for these pixelated pictures because they looked good when I created them, and after exporting it to this HTML, something has gone wrong. But this trend holds. So in all data sets, we have very good nature of the uncertainty, monotone decreasing, and the structure holds. But we assumed two things, right? We assumed that the nature of uncertainty is asymmetric. And the second thing is that we assume that we should use spherical distributions to model the uncertainty. So we did some ablation. Here in green, we have the symmetric version of the approach in which we put adapters on both image and text. So we break this asymmetry. And then we see that the nature is not that good of uncertainty, like it's not monotone decreasing, and you lose recall when the uncertainty is low, which is a bit strange. So this ablation shows that it is empirically, at least, it is good to consider this asymmetricity. And the second thing that we considered was that you should use spherical distribution. So this asympVLMG is the case in red when we use a Gaussian instead of the spherical distribution. And then you see that the uncertainty is still well structured in the sense that it's still monotone decreasing, but we have lost performance. So we have come down by a bit in the recall, right? And this means that when we use a Gaussian to do this, it amounts to introducing a small perturbation to the embeddings because they have now become less effective. So they have diffused a bit, if you draw a mental picture of how it is. So we see that both asymmetricity is important, and we see that also staying true to the cosine similarity and sort of being on the unit hypersphere is important. So to sum up, you can have noise at different levels. It can be within the data, or it can be in the model, or it can also be different in different modalities. And then these have to be sort of handled with care, and these have to be handled differently. And we saw a method, RLVI, which is more suited for training models from scratch under the likelihood maximization assumption. And then we saw asympVLM, which is how do we do uncertainty quantification in multimodal models. And to sort of motivate why this is good, I took these screenshots in August, so this might not still hold true, right? So if you ask Copilot what is 1990 multiplied by 2594, it gives an answer that is close enough, but not completely right. This might be correct now, but when I took the screenshot, it wasn't. I asked Grok the same thing, and also close enough, but the real answer is something different. And of course, now you can say, hey, but these are language models. These are not mathematical models, right? So it's okay to be wrong. But when you turn on the reason or thinking option in these models, then they work slightly differently, and it shows the right answer. So my point of doing or sort of showing this example was that there's always an element of uncertainty or inaccuracy, potential inaccuracy, which is important to consider. And sort of if you look at it in a principled way, then then this can sort of manifest in nice ways and different applications that we might have. Okay, so that's all I had for today. I think I finished a bit early, but that gives us time for questions.
Great, thank you, Prashant. Do we have any questions? You can type them in the chat if so. I don't know if you see Prashant, you're getting a big round of virtual
Oh, thank you so
applause.
much. Thanks a lot, everyone.
Meanwhile, that people are thinking, I was wondering, because you mentioned that for images, you would describe the kind of uncertainty with regards to image data as epistemic. Would you say that's true of all kinds of image data, like even the types of data that's like we are working more with in our project, with it, like microscopy data, for instance?
Yeah, that's a great question. So there's uncertainty in the underlying like physical process, the cells and how they move, for example. But when you take an image at a given point in time, an image is what it is. So when you model that image, the uncertainty comes from, but how was the model optimized and what the parameters were and so on. Of course, we can also include the uncertainty in the underlying process. So we can add it on to incorporate it or do it in a nice way. But this maybe differs for each application type. So if we want to consider all possible uncertainty sources, then we can do so. And then, so that's why I say mainly. I don't say
Right.
completely.
I also have a question, Prashant. Very nice presentation. Sort of related to this question of noise, but there's also specific biases, for instance, in the spectrum of images. Like if you're looking at natural images, they might have a specific uh, like bias in the spectrum of frequencies. And so there seems to be, I don't know if this is a little bit outside your wheelhouse, but is this like, are you thinking about this as well? Because I mean, there's a lot of usage of like pre-trained models that are trained on natural images and then being adapted into the scientific domain. Do you see any potential issues with this or problems with this, given that there might be a mismatch in terms of the underlying distributions in the images?
Yes, exactly. I think this the Huber's model covers it quite well. So um, we train the model with this underlying distribution, natural images, P of C, and then we use it or fine tune it on some other distribution, which may or may not be related to P of C. In some cases, it might be a subset of focus subset of P of C, but in some cases, it might actually be disjoint or sort of have very little overlap. And then doing something like this with an RLVI kind of a thing, that is a principal way to perhaps treat it. But like you say, it's good to be mindful of these changing distributions because then we lose guarantees that likelihood maximization gives us in some way. So it's hard to answer like specifically because you don't know about what P of C or what Q of C might be. But the further away we go from P of C, so for natural images, if that's P of C, the further away we go, the more there is room for noise and sort of prediction variances.
Right. Thank you.
Thank you.
Great. Last call for questions. If you're typing it and just typing a really long question, maybe ping us first so we know that you're still typing, or we can also unmute you. Okay, I see no raised hands, so I guess then we can just end a little bit early and we can thank again Prashant for the amazing talk. And yes, hope everyone has a very nice day. You're getting another round of applause.
Thank you so much, everyone. This was very enjoyable, and I wish I could have come in person to do it at Chalmers. So thank you so much once again for having me.
Great, thanks, Prashant. Bye bye.
Take care then. Have a nice day ahead.